Okay, this is section 3.1, a preview of calculus. What we're going to be doing in this section is just introducing basic calculus topics. And we are introducing the subject of calculus by talking about topics that you already did in pre-calculus and how that is going to extend into a calculus idea. And the way we will do this is with a new operation called the limit. So starting with pre-calculus topic number 1, the value of a function at a point. In this sort of example, you know that f of x is some expression of a function, and you can plug in a value into the x and solve for what the y value is, or the value of the function is at that location. However, in calculus, we're going to extend this to a different idea. I want to know what happens at the function, in f of x near x equals 1. And so this will be a limit as x approaches 1. This is the notation we're going to use. And we're going to talk about each of these topics in detail, so you don't have to know the detail of the topic now. We're going to talk about it in detail and later on in later sections, but this is just a preview. And so we'll understand how you evaluate what is the function near x equals 1, but not at x equals 1. Because at x equals 1, we would just plug in like we did over on this side in number 1 in the pre-calculus topic. Okay, so for the second idea, we talk about slope. In pre-calculus, you could find the slope of a line. Slope is change in y over change in x, or rise over run. In calculus, we will not talk about the slope of a line specifically, but rather I'll have a curve, and I'll ask you, what is the slope at this point? Okay, moving on. We also talk about different types of lines. A secant line is given a function, a line between 2 points on the function. So notice I've chosen 2 points and I've just drawn the straight line between the 2 points. This is called the secant line. Because you know 2 points, 1, 2, on the curve itself and on the line, then you can find the slope of that secant line. That's something that we've done before. In calculus, we'll still have a curve. However, we'll talk about the slope of a tangent line. We'll talk about a tangent line specifically, which is a line that goes through only 1 point on the curve. It will go in the direction of the curve, but it just touches the curve barely at 1 point. Additionally, we have average rate of change. Average rate of change of a function is the change in the y values over the change in the x values. So you will talk about that as f of b minus f of a over b minus a, where your function is the y values, and you'll talk about on an interval from one specific x value a to another specific x value b. Whereas in calculus, we'll talk about what's the instant rate of change. So instantaneously, this means that your A to B interval will no longer be an interval. It'll just be a specific location, one moment in time. A. So you have one specific x value rather than an interval of x values that you look at. So topics 1 through 4 are part of differential calculus. And we'll spend a whole entire 9 weeks on differential calculus. Then we'll move on to something called integral calculus, and that will involve these last few things here. So before calculus, I could give you a circle and you would tell me the area of it based on the radius. In calculus, I'm going to give you a curve, and I'm going to ask you for the area between the curve and the x-axis, and that will require using an integral. Notice there's no formula for how you find the area of that specific shape. It doesn't fit into any of our nice geometry formulas. Okay, before we could find the length of a line segment, how long is the segment from A to B, well, that uses the distance formula, which is essentially the Pythagorean theorem. In calculus, we'll talk about the length of a curve. And so now, if I had a string and I placed the string all along the curve and traced it out perfectly, and then I could straighten that string out and place it along a ruler, I would find the length of that curve AB. We're not going to cover this topic specifically in this course, but it is a calculus topic that's covered typically in a Calc 2 class. All right, volume of a common shape. Again, back to geometry. If I have a cylinder, I can find the volume of it. The volume of the cylinder would be not 1/3, just pi r squared h. It's the area of the base times the height of the cylinder. In calculus, we're going to do something really crazy. We're going to take a curve that comes from a graph. So we're going to graph a curve, and we're going to talk about that area of the curve in the, say, the first quadrant, just like we did in the previous example. But now we're going to take that area and we're going to rotate it around an axis, and we're going to talk about, like, if that area could be the trace, then we would have a three-dimensional volume that would look, I guess, something like a football in this case. And so I'm talking about a three-dimensional volume here, and we'll find the volume of this using calculus. It does not fit in any one specific curve, but it will use something called an integral. Finally, I can tell you a finite number of things to add up. So you could add up 1 plus 2 plus 3 plus 4 all the way out to 100. You could do that addition for me if you wanted, and you could add that up nicely. However, one thing that you'll do in calculus is I'll ask you to add up the numbers. Well, not these ones. Let's say 1 plus a half plus a fourth plus an eighth forever. And it turns out that those infinitely many numbers will add up to one specific number, and you'll find out what that number is. But again, this is a Calculus 2 topic. This number 8 is a Calc 2 topic, and we won't do that in this course specifically, but it is a calculus idea. Okay. All right. Still in 3.1, we're going to talk about the tangent line problem now. These are specific examples that I'm going to want you to do in this section. So we have the secant line tangent line issue. We have 2 points. I'm calling them A, f of A, and B, f of B. I should have a parenthesis there. And I'm talking about a cubic function here. F of x equals x cubed minus 2x minus 2. Find the equation of a secant line. So anytime you need to find the equation of a line, which is something we do very often in calculus, just remember that's something that you've done a lot of times before in algebra. And you're just going to use either slope-intercept form or point-slope form. I will always use point-slope form. It's much simpler to do it for a general point rather than specifically knowing the y-intercept. Okay, so I just need to find the equation, the slope of this secant line. Remember, slope is change in y over change in x. So that's going to be f of 3 minus f of 2 over 3 minus 2, because 2 and 3 are my x values that I've been given here. My function is given, it's x cubic. So f of 3, I plug 3 in, I get 27 minus 6 minus 2. Minus 8, that's 19. Then when I plug 2 in, I get 8 minus 4 minus 2. So 8 minus 6, that's 2 over 1. So I have a slope of 17 here. Good. And now I need a point on the secant line. Well, with the secant line, if you remember, the definition was that I had 2 points on the line. One was from the x value 2, and one is from the x value 3. And so when I plug in, I can choose either of those x values for the location of my point. I'm just going to use 2 since it's easier. And I actually already found the y value, 2 comma 2. And I can just write y minus 2 equals 17, x minus 2. there's an equation of the secant line. I didn't simplify it, but that's just fine. We're going to now find the slope of the secant line over the interval. The slope of the secant line over the interval 2 to 2.5. So it's like the slope that I did here. However, it's a shorter interval. Instead of going from 2 to 3, I'm going from 2 to 2.5. So now, when I find my slope, which is still change in y over change in x, f of 2.5 minus f of 2 over 2.5 minus 2. And I have the same function up there, so I need to determine what f of 2.5 is. Okay, so f of 2.5 is 5.65. Got my calculator and just plug that in. And f of 2 is still 2. So over 2.5 minus 2 is going to be 3.625 divided by 0.5, or 7.25. Now, we're doing the slope of the secant line again from 2, but now to the point 2.1. Notice this x value is still closer to 2. All right, so as I compute my slope, that's change in y over change in x. Okay, so we have a mistake here. Right here, when I calculated f of 2.5, I minus 5, 2. This should be not 5.625, but 8.625. That makes this value 8.625 minus 2 should be 6.625. We're going to divide that by a half. I get 13. Sorry about that. Now on my 2.1, 2 to 2.1, if I plug 2.1 in, I get, I believe, 1.061. So, and then I get 3.061. Then I'm going to minus 2. I'm going to divide by 2.1 minus 2. So this becomes a total of 10.61. Okay, so what's happened, just to summarize what's going on here, I'm going to add a page. Okay, so to summarize what was happening there is I was finding secant line slopes. And I found the slope of the secant line for the function f of x equals x cubed minus 2x minus 2. And I did this on the interval 2 to 3, on the interval 2 to 2.5, and on the interval 2 to 2.1. And every time I do this, my second x value has gotten closer and closer to 2. Here, my slopes changed as well. They were 17 and then 13.25 and then 10.61. Okay, so this is significant because when we go to talk about calculus, I'm going to talk about tangent line. With the tangent line, we only have one point that the curve goes, one point on the curve that the line goes through. And so remember, my point was in question was 2, 2. And my slope changed drastically from 3 from when x was 3 to when x was 2.1. Ideally, what I'm going to do in this section, or in this question, is I'm going to find the slope of this tangent line. And the way that I'm going to do it is I'm just going to cheat a little bit. I'm going to do the slope of a secant line, but my second point is going to be really, really close to my first point. Kind of like the difference between, like in my first point, is 2, 2, my second point maybe will be 2.1 something. Or even better, maybe 2.01 would be even closer, and closer x value to 2 through which I could find a secant line. And so that's what this is the kind of question we're going to see in the homework. So P is my 0.22. Q is my second point on the curve, but it's closer and closer and closer to P. So that's what we say in this part here. As the second point approaches P, the slope of the secant line approaches the slope of the tangent line. And the slope of the tangent is the limit of the slope of the secant line. Okay, so I'm going to go ahead and answer this question. I'm going to find the equation of a tangent line. I need to know a point and the slope. The slope, however, I'm not going to know exactly. We will figure that out once we get into the calculus more. But we're going to estimate it now. We're going to estimate it at 10.61 because that was my slope of my secant line between 2 and 2.1. So then I just need to do y minus y1 equals n times x minus x1. But the m is approximately 10.6. We can do a lot better than that. And in the homework, they're going to ask you how you can do better. And the idea is to do better, I would just need to do a second point just really, really, really close to 2. As in, let's go ahead and do better. Maybe my first point P is 2, 2. And my second point Q, let's just do really, really good. Let's make it 2.001. Let me plug that in and find the y value. Okay, so when I plug 2.001 into the function, I get 2.010000601. And then when I find my slope, using the change in y values, that should be f of 2. I get, this was 2.0100601 minus 2 over 0.001. This value is 10.006001. Now, if I were a betting man, I would bet my slope is 10. That if I get even closer in x values to 2, my slope gets even closer to 10. And so then my tangent line, I should just go ahead and use 10 as the slope there. And that's one of the things we'll do over and over again in calculus. We're going to do one more type of problem today. We're going to do the area problem. This is the idea of finding the area of a curve that is not a nice curve, as in it's not a circle or a rectangle. The curve in question is square root of x, between 1 and 9. So I should keep going here. And let's say that we have 9, 3. And so I'm trying to find the shaded region here, the area of this. To do this, we're going to use rectangles to approximate. I'm going to go ahead and just use 4 rectangles to approximate. It's not going to be a great approximation, but that's what we're going to do. Oh, 4 is a bad number. Oh, between 1 and 9. So let me change this. I only want the area between 1 and 9. So I'm not going to include this region here between 0 and 1. So let's go ahead and use 4 rectangles then. My first rectangle will go here. My and it's between 1 and 3. Then my next rectangle will be 3 to 5, 5 to 7, and then 7 to 9. Notice, I'm not being really careful here, which I should, that these rectangles, I'm using the right value, the right endpoint of the x-axis. So from 1 to 3, I'm using the 3 to determine the height of the rectangle. So this first rectangle here is too high. It's too much area. It does not correctly approximate um, what's under the radical. What is the area? Well, it's the width times the height. And what's the height here? Well, the height I determine by what this y value is right here. And to figure out what that y value is, I just plug the corresponding x value into the function f of x equals square root of x. And so this y value has it's the height of radical 3. And so that's the height of my rectangle. We'll call that A1. And then area 2, the area of my second rectangle, well, that's also a width of 2. And now to determine the height of, so here's my width of 2. To determine the height of the rectangle here, I'm again using an overestimate. I'm going to plug 5 into the function f of x equals radical x to determine the height. So this is 2 times radical 5. And then my third rectangle here has again a width of 2, and now it has a height of radical 7. My last rectangle has a width of 2 and a height of radical 9, which is 3. And so altogether, if I add up these areas, the area is approximately those 4 areas added together. However, that's not the right answer. The right answer we have to use calculus for, but it is a somewhat good approximation. And we can calculate what that is, which is 19.228. So the area is approximately 19.228 square units. And this, I believe, is all that I have for section 3.1. We will go over homework problems in